Oh, I didn't see you there. I was trying to cut up this speeding ticket I got with this ice skate. You know, so how do hockey stops work?
Bad mother.
So, ice skating. You know, the thing, you know, and you put the, yeah, where it's a pretty foreign thing to a lot of people, you know, strapping metal blades and, wait.
Are you coming down?
What are you doing?
Strapping metal blades onto your feet to glide across frozen water, it's pretty weird. But I mean, I've been playing hockey since I was like 6 years old, and it's about as easy as walking for me now. So a key move for hockey players is the hockey stop. Hockey is a fast-moving sport, constantly changing directions, and hockey players have to be able to stop on a dime. Slowly turning around isn't really an option for them. But how exactly does a hockey stop work? If a hockey player digs their blade into the ice, shouldn't they just flip over because of the friction that's created? And although this hockey skate might look like some weird knife strapped to the bottom of a boot, it is a little bit more complicated than that. To begin, maybe we should understand exactly what skating is. Skating isn't a blade gliding across ice. Well, it is and it isn't. The blade melts the ice and creates a fine layer of water, and that water has such a low coefficient of friction, it allows for the skate to easily glide across it. So while the end result might be the skate going over ice, it's actually coming into contact with a very thin layer of water. The other important thing to understand before we actually get into talking about the physics behind a hockey stop is what exactly a skate blade is. Now, if we look at the edge of this knife, it is thin and clearly only has the one edge. This is much different than a hockey skate, which actually has two distinct edges. But if we look at the hockey blade, it might look like that when it contacts the ice, it goes straight down and creates a square-like shape. In actuality, it's a concave shape, creating two distinct edges. So it's hard to see on camera, but you can see how there's a rise and fall in the middle if you look close enough. Players have the option to have their blades cut with a deeper radius. The deeper the radius, the worse the skate glides, and the more effort is required to keep moving. The trade-off is that the deeper cut allows for tighter turns and faster stops. When it comes to hockey stops, the deeper the cut, the more the blade digs into the ice, and the faster and easier it is to stop. Now that we understand how skating and skate blades work, it's time to talk about the hockey stop itself. When a player begins their hockey stop, they turn their blade sideways and begin shaving off the top layer of ice. This creates a shearing force. A shearing force occurs when a force is applied at a perpendicular angle to a static or non-moving object or material. The formula to find a shearing force is T equals Fa, or the shearing force equals the force divided by the area the force is being applied. In our case, I weigh around 145 pounds, and we can estimate I'm traveling at around 7 miles per hour, or 3.13 meters per second squared. Skate blades are estimated to be around 50 microns thick, or 0.05 millimeters, and skate blades are on average 295 millimeters long. And we can estimate the distance it took me to stop was about half a meter, or 500 millimeters. Now that we know all of our values, we can place them into our formula and change them to be all uniform units. Once we do some calculations, we find that the total shearing force was 61.54 pounds per millimeter squared. Now that you understand a bit more about the science behind skating, maybe it won't seem as foreign and you'll give it a try.